Alright, so here's the thing. In the real world, we don't do everything in bomb calorimeters. We do things in an open lab, and so most of the time what we're actually interested in is the heat part of internal energy. We're not so much interested in the work. So when we have delta E, Q plus W, now when we can, we'll use them both, but if we're just doing a chemical reaction back in lab, the Q part is all that's going to matter. The work, it's going to be done, but it's not really going to matter to us that much. So we have this thing called enthalpy, and enthalpy is the measure of just this heat. Now, this sometimes confuses people because when we do bomb calorimetry, everything is coming out as heat, but it's the work and the heat together coming out as heat. With enthalpy, now the work is happening, it's being done, but we don't care about it, and so we're focusing on just the heat component. So remember that work was negative P external times the change in volume. So basically what this equation is saying is that enthalpy is equal to the change in internal energy minus the work. So it'd be like rearranging this to say Q is equal to delta E minus W, because this right here is the opposite of W. So it's just the heat portion. Yeah. So what's the difference? Well, internal energy is a measure of all of the energy, both heat and work. Delta H is just the heat under conditions of constant pressure. So if you have constant volume, like I said, the work and the heat are coming out together. But in this case, well, I guess to say the work and heat are coming out together is wrong. There is no work done, so all the internal energy is coming out as heat. With enthalpy, work is being done, we just don't measure it. We're only worried about the heat. So the more gas produced in the reaction, the larger the difference between those two values. Sometimes they'll be really close, but the more gas produced, the larger the difference, because when you produce gas, you're going to be causing volume changes, and that's work that's being done. So here's a question. You have butane burning, you got 1 mole burning. It produces 2,658 kilojoules of heat. Since it's producing it, it's giving off negative 2,058 kilojoules. Okay, it's negative because it's producing. If it does 3 kilojoules of work, that's also negative because it's doing the work. What are the values of delta H and delta E? All right, well, delta E, remember, is heat plus work. Delta H is just the heat. Well, in this case, this is the heat right here. So delta H is equal to negative 2,658 kilojoules. Heat plus work would be negative 2,658 plus a negative 3. So delta E would be equal to negative 2,661 kilojoules because you put them both together. So hopefully that makes a little bit of sense. It's not that complicated, but it takes a minute to kind of think through. A positive change in enthalpy means heat is flowing into the system. We call it endothermic. So if something is cold to the touch, it's endothermic. A negative enthalpy change is heat flowing out of the system. That would be exothermic. That would be hot to the touch. So sweat evaporating from skin, sweat is absorbing heat, so that's endothermic. Water freezing in a freezer, that's water giving up its heat to become colder, so that's exothermic. Wood burning, anytime you see something burning, that's going to be exothermic. So number 3, and gasoline burning, number 6. Exothermic. An ice cube melting, that's actually gaining heat energy, that'd be endothermic. An ice cube is cold to the touch. Nail polish remover evaporating, same sort of deal as the sweat. Since it's evaporating, it's taking in heat, so that would be endothermic. So anytime something's endothermic, positive sign, negative sign for anything that is exothermic. The source of this thermal energy is going to come from the chemical energy, the potential energy that's held within the bonds. breaking bonds requires energy. You have to pump in energy to break bonds, but then forming bonds releases energy. So when an exothermic reaction happens, it is overall giving off more energy than it took to start. In an endothermic reaction, it's taking in more energy overall. So what is the source of this? Well, it's all the bonds and interactions that are going on. So it comes back to Coulomb's law a lot of the time. So whenever you're looking at things, wondering where all this energy comes from, remember we have potential energy within molecules. It comes from the bonds, it comes from the intermolecular forces, it comes from all this sort of stuff, and it's there, but we don't recognize it a lot of times. So it can be a little tricky. If you are asked a question and you're not really recognizing where the energy is coming from and it's not obvious, start thinking about the potential energy involved, all those interactions. All right, I think we'll stop there for this one.